Alright, we are back again. Uh, Welcome back if anyone's watching. Yeah, so here we are. Direct mapped cache interest calculation. Okay, this is index. Which line in the cache to use? Got it. Cache size by block size, right? Let's say there is 16 MB for cache, obviously rough calculations, and one block takes 1 MB, then there will be 16 blocks to choose from. So that gives us the address of the cache block, and this tag because it is multiple blocks of RAM are associated with a single block of cache. The tag bits are the remainder of the address. Use to verify a cache hit. So tag will be calculated at the end because we don't know how much space is there for that yet. And there is offset is like pinpointing the byte, right? So what is the size? 16, right? 16 bytes. So you need 4 for offset, and total 20 it was given. See, total 20 was given. Yeah, 20-bit memory address system. So 6-bit per address. And how many of such addresses are there, right? There are like 10. Alright, 2 power 10. What is the 2 power 10 indexes? 6 into 2 power 10. 1024 times 6. 6 4 the 24 to 14. 6 1 4 4. 6 into 2 power 10. That's it. 6144, right? That's it. That is all we wanted. We did it. 64 general purpose registers. Okay. 50 distinct instruction types. Instruction is encoded in 32 bits. Maximum number of bits can be used as immediate operand and the given instruction. Add R1 25. R1 is equal to R1 plus 25. Obviously. Calculating immediate operand size. Not deserving for 2 marks. While allocating 6 bits for opcode, 6 for registers. We need 6 bits to represent registers. Okay, 6 bits to represent opcode. Okay, we have 32 bits in instruction. Opcode register. Operation code, it might be 32 minus 2. Maximum 20 bits can be used to store immediate operand. What is he saying now? Expanding opcode scheme. Yeah, my guy is on to something. Okay, I don't know any of that, but so from this data, right? So maximum number of bits 32 total. So register 64. So you are going to need log 64 to the base 2. So what's that? 2 power 2 square. Okay, mean 2 power 6 64. That's it, right? 2, 4, 8, 16, 30, 60. Yeah. So 50 is between these two. So 6 for opcode, and you are going to immediate operand. How many bits? How many bits? 6 plus 6, 12, 32 minus 12, that is 20. So what did he say? Yes. Okay. So what he is saying is one instead of 6 per opcode. I don't know, but it was never specified. So you're not supposed to think like that. I think. Here we go. Computer has two processors. Sorry, two processors. Yeah, four processors. CPU based. Alright. And these are only processing system. The scheduler uses non-preemptive priority scheduling. The M1 uses priority execution for the process. P1 has highest and P4 has lowest priorities. Round of execution of process. Yeah. As process PI is scheduled to process MK. If the processor is free, no other process is waiting with higher priority. At any point of time, a process can be allocated to any one of the free processes without violating the execution priority rules. Ignore the context system. Average waiting time. Average waiting time. So should we track the manual way? Like first P1 will be, so this is M1 processor and this is M2 processor. P1 will be executed to this and P2 will be executed to this. Okay. Why I hate error keyboard. Dual processor non-preemptive scheduling. Okay, initial P1 20 ms, P2 P1 P3, P2, A4. Kind of understand what's going on. Precision at T is equals to 20. Both processors are free. What is this one called? Yeah, just like we thought, dude. The P1 and P2 will be allocated. Right. And you also, suppose to write the waiting times. CPU bus 2016 2510. 2016 25 and 10. So if you see P1, P3, P2, P4, P2, P3, P4, P1. That's good actually. So P1 takes, no, what did I write? Yeah, M1, M2. Okay. So P1 takes 20 seconds, P2 will be completed, and after that, P3 will be executed. At 0 seconds, this 2 will be initiated, and at 16 seconds, so P3 waits for 16 seconds, and what will happen after that? So P1, okay, P3 takes how much time? P3 takes 25 time. That is 16 plus 25. So that is 35, 41. Yeah, so we are not completing. So at 20 seconds, right? At 20 seconds in the priority, P1 is done, P3 is there, P2 will be put over here, and P2 will be completed at 20 plus 16, 36 seconds of time. So P1 and P2 no wait time, and P4 took 20 seconds. That is 36 seconds, and by 4 that is 9 seconds. Wow, I solved it. Okay, I don't know his. Yeah, it is a databases question. And I say ID, I got it. So relations describing teams and players of a sports league. Team ID and team name. Player ID, player name, and team ID. Tuple relation calculus. Queries written the name of the players who play for team having T name is equals to N1. Okay. We don't know tuple calculus. So we are supposed to know that. Let's try this. So what do you name it? Name of the players who play for team. You need player name who play for teams. Who play for P dot P name where P belong to okay players and existing such that yeah certain and okay only when all the basics of topper calculus so explain them and answer this question simultaneously too. Declarative query language used in databases. How to fetch data. You describe what you want. Variable. Tuple variable. Tuple variable. Predicate. Example. Student is a table with attributes name and age. They belong to student and membership. Attribute access. Recall connectors quantifiers. No, you messed up. You messed up with the question. So we need to return the name. Team contains the players and the exercise such that T belongs to teams and the player T belongs to teams. P belongs to okay. Schema recap. Schema messages maybe. Good. P dot alright. Select players from players where there exists a team with same select player names from players where there exists a team with the same team. Where there exists team with teams has no attribute P name. Good. Semantically invalid. Select player from name players. Select player names from players. If there exists a team named M1. Okay, we will debug this, dissect this tuple. P dot P name, P belongs to players, and exists is such that T belongs to teams, and player dot TID is equals to team dot TID, and T dot name, team dot T name is equals to MI. MI. Okay, the problem with the second one is P name is not in T. That is a problem with second one. And with the third one, T belongs to teams, and T dot T name is equals to MI. All players of MI are returned. Okay, don't confuse with players. All tuples with MI are returned. Not the current playing players. So you need to have a deeper understanding of schema. This is like instantiation or giving a connection between the player table and the what and the teams table. A packet with destination IP address and set a router whose routing table. Which interface will this packet be forwarded to? Subnet. Uh, I don't know. I really have no idea. Yeah, the fact that it is for 2 marks makes a lot of sense. A packet with a destination IP address. Which interface will be forwarded based on the routing table below. CIDR notation. Classless interdomain routing notation represents the subnet mask. An initial. The longest prefix match route. And the router has multiple matching routes. The longest subnet mask. Okay. How are they matching out? Uh, you are given a destination IP. The router has a routing table with the subnet addresses and masks. To decide the interface, the router uses longest prefix match. Among all possible subnets, pick the one with most longest prefix. IP addresses are written in dotted decimals. First 10 bytes are fixed. Do bitwise and whatever. This is 8-bit representation. CDR notation. Okay.
అరే నాకు అది పెట్టరా దాన్ని పడతా
Wow. So, and Andrews. Okay, thank God. I think I kind of understood what's going on. Subnet. Mm. So, if that is the case, Okay. What is that rule again? Longest prefix match. Longest prefix match, yeah. Let's start from the biggest one. 145.36.255.0 and with a subnet mask of 24. Destination is 145.36.109 points. And say somebody wrote it. Oh no. You're supposed to convert that to binary. Okay. 72, that is 1, and 36, that is 0, 18, that is 0, 29, that is 0, 24, and 22, that is 0, 21, that is 0. So that is 100, 100, 01. Is it not? Yeah, it is. 36 is 100. That is bad at white bit. And what else do we need? 109. 54. 1 and that is 27. 2, 13, that is 1. That is 1, 2, 3, 6. And that will be 1, 1, 0, 0, 1. 1, 2, 3, 4, 5, 6, 7. What did you do? 1090 11101 points and similarly you do that. To 55 2, 3, 4, 5, 6, 7, 8 and 4, 13, 4 and past 16 20, 21, 20. Alright. Bitwise and 1 and 1. Okay. You motherfucker, that's not how you work it out. 255. That makes sense. So this is the IP that you need. And now if you look at 18, 145 is matching. 145 is matching. And 64 and 109. This is okay. 64. It is like 1, 2, 4, 8, 16, 32, 64. That is it. And what is 109? 109 is something like this. You already did 109? Yep. Matched. Done. Oh my god, that took like forever. So this is a two-by-two matrix. What the heck is A13? Okay, that's A power 13. Highly impractical. Find the eigenvalues. Get the characteristic. We should check it out. This should work out. 1 minus 1. This is the matrix. 1 minus lambda. Minus 1 minus lambda. Get the characteristic equation minus square plus lambda into trace, that is 0. How do you find the eigenvalues of a 2 by 2 matrix? We just learned for 3 by 3 dot. That's it. So done. Determinant of A minus lambda I. Get the characteristic. That is it. So that's CAD minus BC. So it will be minus 1 minus lambda plus lambda plus lambda square. And again minus 1. So that's lambda square minus 2 is equals to 0. Here is equals to 2. Lambda is equals to plus or minus square root of 2. Okay, these are the eigenvalues. So for power 13, they will be plus root 2 whole power 13 minus root 2 whole power 13 2. 2 power 13 by 2. The 2 power 6. 64, 64 into 64. Okay, I kind of got it. For variable Boolean function in the SOP form, function is calculated for bit binary number, more significant bit and less significant bit. No don't care terms. Minimized Boolean expression. Why don't we, try drawing the K-map for this one? It should be easy. Yeah, that's messed up. That checks out. Yep, that checks out. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right. So 0, 2, 4, 8, 10, 2, 4, 8, 10, 11, 12. You can, map like this, and you can map like this, and you can map like this. So yeah, B3, B3, B2, B1, B0, B3, B2 bar, B3 bar, B2, B3, B2, B3, B2 bar, B1, B0 bar, B1 bar, B0, B1, B0, B1, B0 bar. So if you look at this, everything gets cancelled. B1 bar, B0. We already got the term, did we not? A is the answer. Let's see. And here B bar, B bar not cancels out B1. B1, B3, B2 bar. B1, B2 bar, B3. That's correct. Got the answer. Wow. And B1 bar cancels out and B0 bar. Oh, what? B0 bar, wait over. Okay. A should be the answer. Oh, I see. Oh, wow. You can map the corners. But got it. Got it, yeah. Good. Okay, undirected weighted graph with 100 vertices. Number of edges and the shortest path between U and V. Maximum value U is not equals to V is 30. Okay, let T be any breadth first search. Which one of the options is correct for obviously having a sample graph doesn't hurt. Let's see what we got. Undirected, unweighted. Okay, number of edges. Let's have some graph like this. Why not? This is, let's say, U. This is, let's say, V. And 100. There will be hundreds of vertices. So maximum value is 30. Breadth first search. The height of the tray. If you okay, this is not actually minimum. This is minimum. So if you look at this, this is a maximum path. Max is equals to 15. So height If you take this as V, right? It will be 1, 2, 3, 4, 5. Can it be greater than 15? BFS rooted at vertex of that is a conclusion that we got as well. That is the conclusion that we got as well. Alpha, beta, A, B closure, A, B closure. Regular languages. The problem with alpha, beta, alpha is if you alpha, beta, alpha. Both are actually same, right? What the fuck? L1. Okay, ouch! The intuitions can be wrong most of the times. L1 is not regular and L2 is regular. Oh yeah. Well, let's see. All right, people. We did not solve a lot of questions, but still, it's good. All right, people. I need a break.